Wait, okay, sweet, we're good.
Good. All right. Well, thanks for coming out, everybody, on a rainy night. I appreciate that. And hopefully you'll leave having learned at least one new thing, and I'll do my best to keep this entertaining while we dive into some interesting abstract things about cybersecurity. So I'm going to open with a story, and just to protect the identities of the innocent, I may change some names here, but just bear with me. So Mr. Orange is having a bad day. He can't get to his offshore Cayman bank account, and he's been trying and trying, but nope, not having any luck. He's using his nice secure password, Your Fake News, and he's not having any luck. And he's getting desperate because his handler is demanding payment. That would be Mr. Red. So Mr. Orange decides, all right, I'm going to raid my fake charity accounts that I have some extra text message cyber thingy on. That should be safe. I'm going to go to those banks, but he's on Air Force One, so no cell reception. So he sends a few tweets. They land. Cell phone starts working. He's getting messages that funds are being drained from all of his accounts. That is not good. So he calls Sarah Huckabee Sanders, fix it for me. But nope, all the funds are gone. Looks like a hacker got the best of Mr. Orange. So in all seriousness, what happened? I mean, he had actually a reasonably secure password. If you check it on, say, howsecureismypassword.net, 610 trillion years to hack Your Fake News. And he did have SMS verification on some of his accounts. So, how did he get compromised? How did the funds get stolen? Well, his bank details, email, etc., Ashley Madison hack. Password fairly easily guessed from social media. Or perhaps stolen from Twitter's logs, where they actually were storing people's passwords in plain text for quite a while, although they claim that information was never accessed. A skilled Mr. Orange impersonator was able to do a SIM card swap for his cell phone. Therefore, all of the backup text messages were coming over to the impersonator rather than to Mr. Orange. And he reused the same password on all of his accounts. So once they had that information, it was open season. And in all seriousness, SMS verification really does have issues. Obviously, you have the no service problem. Foreign country, you're in somewhere in the bush in New Zealand, or you're at an Airbnb that has Wi-Fi but no coverage. SIM swapping is for real, and the worst thing about it is, even though providers have gotten better at requiring extra hurdles, the reality is it's not that difficult to scrape somebody's information, call up a provider. Oh, I had to switch my phone. Here's my my email address or whatever. U.S. Social Security number, that kind of thing. And then, yep, you get the phone number switched. It is possible to intercept cell phones. The network that they run on the SS7 was developed in 1975. It's full of security holes. It's been in the news. In reality, that Mr. Orange is being listened to by the Chinese and the Russians in real time, which is really scary. Stingray towers can intercept calls. And the other thing that's interesting is it's the equivalent of reusing your password, because if you use the same cell phone number for all of your second verification and somebody's compromised your cell phone, then they have your second factor on all of your accounts. So it's not really that great of a protection. And had fun at the expense of Donald Trump, but these really are affecting people. Adam Draper blogged in Medium how he had $50,000 stolen by somebody who hacked his Gmail account. In his case, he only had password protection, but once they had his account, they started sending invoices to his accountant, who happily sent money to a third party, not realizing it had been compromised. Megan Clifford lost about $3,500 and pretty much a month of her life trying to straighten things out. And in her case, her phone number, her SIM card and her password were stolen, probably from T-Mobile in the Experian breach of 2015, although T-Mobile was hacked directly a few years later, so it could have been then as well, or a combination of both. And in 2011, approximately $1 billion was stolen from small businesses due to compromised usernames and passwords. And those figures are from Symantec, who estimate that 70% of those businesses go bankrupt when that happens to them. So this really is a real problem. And of course, you don't have to Google very hard to find plenty of stories. They're in the news all the time of these kinds of things happening. So some of the other problem is users remain uninformed about the risks. It's obviously a real problem. Wombat Security in 2018 did a user risk report of about 6,000 adults in 6 or 7 different countries in Europe, Australia, and the US. And they found that 67% of the respondents do not use a password manager. And of those 67%, about 21% were reusing the same 1 or 2 passwords, another 46% using same 5 to 10, and probably in some kind of a pattern of, oh, I'll use a secure password for my bank and an unsecure one for the rest, or something like that, that kind of a pattern. What's also interesting is users are biologically wired to make predictable password choices. In her book, Mindfulness on the Run, Chantal Hofste talks about how the human brain does what's called top-down processing. And what it does is an energy-conserving mechanism where once your brain starts learning patterns, it wants to automatically reuse those. And so I suspect that simple reused passwords are in that top-down. People, oh, I don't feel like dealing with this right now, tick, and away they go. The other thing that's maddening is there actually is, we do have two-factor authentication. It's not offered enough. So if I go check this site that lists where two-factor is available, this is for banks. And hopefully you can see with the contrast, but there's a lot of red in here. A lot of banks don't offer two-factor authentication. And we really want to make it challenging for our malicious parties. As developers, we need to honor the trust that's placed in us. We really need to try and secure user data. We need to limit damage when a breach happens. We need to try and do a better job of informing users and educating and coming up with ways that is easier and easier for users. Because, until we have robot overlords, most hackers are people. So they have limited resources. They have limited funds. They have limited time. So the harder we make it, the more likely they're going to give up and move on. Probably will never solve it all the way, but again, anything we can do to make it harder. So I'm giving this talk because I'm frustrated. I can tell you that I have banks here and in the US, Investment, KiwiSaver, none of them have proper two-factor authentication on them. And I thought, well, I'm a developer. I need to learn more about this. I'm aware of the mechanism I'm going to talk about, but I wanted to learn more about it. And what I found is that good security, not surprisingly, it's tricky and it's time consuming. So I have a demo app we'll look at briefly, but it took a while to code that thing up. Admittedly, I was, hand doing some of it so we can see how the calculations are done. But still, it took a while. It took me reading 5 or 6 of the RFC specs around the authentication mechanisms to get an understanding of how they work. And of course, lots and lots of supplementary documentation and articles. We want to keep up to date as developers because, as we'll see at the end of the talk, there's interesting new protections coming out in all areas of security, not just authentication. And we want to try and use the newest, best protections when we can. And obviously, again, based on my experience of deliberately hand coding, we want to use existing frameworks. The work has often already been done by experts in the field. Now with the new .NET Core, I can stand up a new website and just say I want a second factor, and it sort of codes everything up, automatically sets up an identity database, and it's ready to go. Azure AD has a multi-factor built into it. I'm more in the .NET realm, but I'm sure that's available in PHP realm and so on. We want to try and use what's there when we can. So when we're talking about an ideal situation, an ideal solution, the usual issues, right? Ideally, it needs to be easy because people already are struggling just with passwords, let alone something else. We want to, again, I mentioned, we should start considering better documentation, making this more available. those of you who are familiar with some of the multi-factor stuff, at least my experience, when it's there, it's buried in a menu somewhere. You got to go in, know when to go into your profile and find the security, security settings, and then add it. And again, the average user who's not very technically savvy is never even going to think to do that. And when they do get there, they're going to be like, "What is this? I've never seen it before." We need to be cheap because already people are strapped a lot. You don't want to have to pay for a $500 third-party token to do what you need to do. And again, as developers, we need to make sure what we're doing is we're providing additional layers of security. We're just making it harder and harder and harder for malicious parties to get in. And so we need to consider architecture. We need to consider how we're storing information. Passwords is the obvious one, but we'll see this implementation has a key that we need to be careful of. Any pertinent security or user information. So this talk is about multi-factor authentication. So what we mean by that is that there are 3 key factors we typically talk about. The first is knowledge. So the idea is it's something only a user knows. So again, this is your password or your PIN or something like that. And again, ideally only the user knows this. It's not stored somewhere else, or if it is stored, it's stored in a way that's secure enough where the chance of being able to break it is almost zero, or zero ideally. The second is possession, something only the user has. So this is where we get into a mobile device or a third-party fob. Or if you think of an ATM, it's your debit card. You have the PIN that you know and the debit card that you have, and that's how you can get at your money. And the third is inherence. And this is where we're getting into biometrics, something only the user has. So your thumbprint or your iris. But it can also be a pattern. So the way you type or the way you move your mouse, things like that, with the new AI and the new processing power, starting to see, and again, at the end, we'll talk about that a little bit, where we can actually get profiles of people's behaviors that's distinct to that person. So then when we talk about multi-factor, it's the intersection of these things. So two-factor, you might have heard, it's really just a subset of multi-factor. And this talk is going to focus in particular in the intersection between knowledge and possession. So what we're going to do is we're going to talk about a possession factor, which uses a mobile device, or it could be a hardware key. So the image on the right is the RSA Secure ID, which has been available for a while. It provides the same mechanism that we're going to talk about here. So that would be something only the user has. And obviously this would be combined, say, with their password. And the mechanism is called the time-based one-time password, or TOTP. And this is a software token, meaning it's calculated on the device. So when we talk about a one-time password, that just means it's valid for one transaction and one transaction only. So the advantages of this, can't reuse it across multiple sites because ideally this is a randomly generated password that, the odds of it being reproduced for a user is almost zero. And it's not vulnerable to replay. So in other words, once you've authenticated with it, somebody else happens to have stolen it, they come in a few minutes later, try and do the same thing, they can't, even though it's a valid password, because once it's been used, it's done. Or some other mechanism to expire the password. So a subset of this is the HMAC-based one-time password, HOTP. And this is really the kernel of what we're going to be looking at in more detail today. So the idea is you have a counter of some kind, you hash the counter, and then you have a secret key that's used as part of that hash. And this gives you a value that the user can exchange as an authentication. The host site does the exact same calculation because it has the same secret key and it can calculate the time the same way. And you get a comparison value that you can compare hashes and make sure they're the same. So then the TOTP is HOTP, and the only thing is that the counterpart is time-based. And so instead of some other auto-incrementing mechanism or something like that, it's just using the clock as a way to count up and get a counter. So if we go back to our objectives, the authors of the HOTP and TOTP took this stuff into consideration. It's interesting to read the RFCs and see that they talk about some of this. So they specifically say this has to be easy and readable, easily read, easily entered. So they recommend 6 to 10 digits maximum, and they recommend numeric only. Now, admittedly, the HOTP was 2005, so a lot more, old school mobile phones with typepad only rather than smartphones, but nonetheless, it's still valid. They also talk about how the hardware has to be cheap, and that means also we want to minimize battery usage. We want to have low computational power required to be able to develop these tokens, and it needs to be secure. And in this case, we actually hash twice. And yet the algorithm is fairly easy for a developer to implement. And so the process, many of you have probably already seen something like this, but the general idea is you download an app to your phone, or you buy an RSA ID, something like that. You do your normal registration, username, password, etc. Then you get a screen with a QR code. You scan it into your device. Then your device calculates a 6-digit number, and you go, cool. You enter that in at the prompt. Then you're registered, and then from that point forward, whenever you log in, you have the same thing. You don't have to rescan, but you get what's the number on your phone, you look it up, you type it in. So we'll look at all of this now in more detail. So the first bit is the register secret key. So the host creates a unique secret key. So advantage over user coming up with something, the host generates a nice, strong, secure random key. It's displayed as a QR code. I think this is partly for ease, but it partly is a way to sort of obfuscate. And then you scan it, so your device gets that secret key, and then the rest moves forward. And it's important to have a manual option here as well, where it displays the secret key on request, kind of like show my password. And the idea there, I believe, well, clearly it's either you don't have a QR code scanner, or maybe you're already on your mobile device and you're registering for the first time, so you can't scan it. So you need to be able to enter the key into your phone. So what's in the QR code? So it's a standardized URL, always starts with OTP auth. This was, as far as I know, developed at Google, by the way. Then you have a type, which is going to be either HOTP or TOTP, a label, and parameters. So what you end up with is the issuer name and the username are included, and the issuer name ends up being in there twice. I'm not quite sure why, but I have noticed on my mobile apps that depending on which app I'm using, sometimes you need the issuer name, oh, I guess my pointer's not working or can't see it. You need it as part of the label. Sometimes you need it as part of the parameters. The only one that's required is a secret. The issuer is strongly recommended, and the rest are optional. This is more, I think, forward thinking, because I think most of the Authenticator applications actually don't implement anything around the number of digits. It's always 6. The period is always 30. We'll get into that in a minute here. So here's a real world example, maybe from GitHub, where we have a secret key. We know it's GitHub, and then like on my app, when I pull it up, I know, because I'll have multiple, obviously, and I can tell which one is GitHub because it's registered through this. What's that? That wouldn't be your real GitHub. No. Not even the real email address. So that would be funny though, wouldn't it? So the secret key itself, there are some requirements. It needs to be at least 128 bits and recommended 160. This is for in the hashing requirements, you need your key to be enough of a length so that the hash is sufficiently random. It needs to be generated randomly, and critical, here's a case where a developer could make a mistake. It has to be unique per user. So it would not be all right to go, well, cool, I've got a nice long randomly generated key, but you store it as a constant or something, and then it's used for everybody, because that makes it much easier to then reverse engineer the hash. And it's also a base 32 encoded string, which I found interesting, but there's actually some good reasons for this. And so what base 32 is it's a limited alphabet. And if you look at the characters, first of all, they're all uppercase. And secondly, it's missing 0, 1, 8, and 9. And this is to avoid the problem of characters that are confusing. So is that an O or a 0? Okay, when you're using base 32, you avoid that. And this, I think, goes back to the part where you need a manual option. This way, if you do need to enter it manually, it's much easier to enter it correctly, because it's already sucks to have to type in 20 or 30 characters or whatever on your phone. We also have to, again, as developers, we have to be careful of the storage, because this is, if you can't tell already, this is the linchpin. This key is the bit that makes the magic happen. So you need to store it encrypted. Now, encryption is not the same as hashing. If you encrypt something, that means it can be reversed. It can be decrypted. Now, ideally, you use something like AES with CBC that really encrypts it, but it's not as secure as a hash. But it has to be able to be passed in plain text, so you don't have the choice of hashing the key. You also want to compartmentalize it. And what I mean by that is that you don't want to save it, ideally, in the same place that you save the user's password. Because again, if you have a skilled hacker who gets in and they get the passwords, you don't want to be able to grab all the secret keys at the same time. Ideally, you compartmentalize it. You store it in a different database. You store it, some online location. I don't know. Or at least you granularize it. And all that means is that it's in the same database, but you need a different user account to access that particular table. So you have a connection string that's different. So maybe a hacker's obtained a connection string, but they can only get at the passwords, or they can only get the secret keys because they don't have all of the passwords, connection strings. So now we go to the token step. So this is where we enter it. So again, it's real basic. Now we have the secret key. We both have the same time. We calculate the value on our phone. We type it in. The host does the same calculation, and it's the same as a password mash. We're comparing hashes, and we go, yep, it's 000042 on both sides. You're good to go. Okay. So how does this work? How does it calculate a 6-digit number that's random and unique and unreproducible? So what we do is, again, I mentioned we've got the current time, which is expressed as a counter. We have the secret key. We do a cryptographic hash, and we get a 6-digit token out magically, right? So here's the first bit, the counter. Here's the formula on the left. So what we do is we calculate the time in seconds since the Unix epoch. And the Unix epoch is defined as January 1st, 1970 at midnight. And that's pretty much a universal standard. So every system can calculate the number of seconds since then. And then we divide that number by our time step duration, which is typically 30 seconds. And I'll explain why in a second. So that's the basic formula for our counter. So every 30 seconds, it increments. Okay? And so why do we have this time step? Well, the big one is usability. If the counter generated a new token every second, obviously the user couldn't possibly enter it in time to make it usable. But we also have to worry about time drift or clock drift or network latency. So, the phone may not be quite in the same time as the server, or it's a slow network connection. So by the time the number is entered into the form and sent to the server, enough time has lapsed where the server's calculation is off by 10 seconds and goes, no, that's not valid. And we also have to be careful about security because this is only a 6-digit number. And so, if you plug that number into the how secure is my password, it's like microseconds to crack that. So brute force is really the only viable option short of stealing the secret key. And so we have to make sure that we do some throttling or a lockout or something like that. You try the code 3 times and then you're locked out, whatever, like a invalid password. The other thing we do with this to deal with the clock drift is that often the sites will allow several time steps that are consecutive. So essentially you give, say, a 1.5-minute window rather than 30 seconds. And that gives a pretty generous amount of clock drift. And I suppose you could even get fancier and figure out that user A is always 20 seconds late. So you shift theirs accordingly or something. But that's the general way. So again, even if you give a 1.5 minutes, but you combine it with throttling or lockout, then it's figured to be secure. So getting into more detail now. So what we do with the counter, again, it starts as just an integer. We actually decode it to a big Endian byte array. And big Endian was one of the terms that I didn't understand, but it's actually a very simple concept. It just means that the most important byte or piece of information is at the beginning. So if you think about a number, if you change 1 million to 2 million, that's a much bigger change than changing 100 to 200. So we're talking the larger numbers are more important. And actually the most important is the sign, because going from negative to positive or vice versa is even a bigger change. And one of the reasons for big Endian is to strip away the sign. And the other, I think, is just to make sure it's predictable. We always know what order these bytes are going to be in because it's declared they need to be big Endian. The secret key itself that starts as that, it looks like a string of base 32 characters. You actually decode that to a base 32 byte array. Then we use the SHA-1 hash. We hash the counter using the key. Then we do a second hashing by doing an offset and a truncate on the result. And then finally, we're able to extract the 6 least significant digits to get our 6-digit number. So I'll explain all of these in detail, but those of you who are familiar with security, you might be going, why are we using SHA-1? That one has been broken. And as far as I can tell, the answer is there are a couple pieces of that. One is that SHA-1 is not recommended for storing passwords. And I think it's because, a stored password is static. It can be, somebody can work away at trying to crack it. Remember, these are only valid for 30 seconds. So you still have to figure out how do you crack a SHA-1 in 30 seconds. But I think also more importantly is it's not just a SHA-1 hash, it's then rehashed again, and we'll see how that's done. So I know you can't read the small letters, don't worry about it. The main thing is I just wanted to show is we have a number, the counter, it ends up being a byte array, the secret key that started as a string is a byte array, we get a hash with a digest, we do an offset and truncate, and what we're doing is we're ending up grabbing some of the bytes out of the results of the SHA hash, and from there we extract our final number. So the way we get the offset is really interesting, I think. So in the SHA hash, again, there are 20 bytes. They go to the least significant one, and you take that and then you do a binary AND against the number 15. The number 15 is 1111. And when you do a binary AND, you compare the ones and you only keep the ones. And so what we're doing is we're stripping out anything that's larger than the number 15. And we're guaranteeing we're going to have a number that's between 0 and 15. And the reason that's important is because what we use this offset for is an index position in the SHA hash, because now we're going to go back into the hash, start at whatever index position comes out of this sort of randomly generated index position, and we go from there. The SHA-1 hash is only 20 members, so we need an index that's smaller than 20. And in fact, since we're going to grab 4 bytes, 0 to 15 is a pretty good random number that guarantees this is always going to work. Then what we do is we're going to do essentially 2 calculations to truncate the hash. And we use a combination of a left shift and a binary OR. And what a left shift does is it just literally takes the ones and shifts them to the left however many positions you specify. So 13 left shift 3 would end up being 104. And you can see how the orange numbers have shifted to the left 3 positions. What you're actually doing is multiplying 13 times 2 to the 3rd. So if I did left shift 5, it'd be 13 times 2 to the 5, to the 5th. So the reason for the left shift is going back to the spec. It needs to be computationally fast. Left shifts are faster than multiplication when you're getting down to the processors. So that's why we're doing it this way. Then the binary OR is similar to binary AND, but as you might expect, in this case, if there's a 1 in either number being compared with an OR, then that 1 is kept. So 13 OR 65 would be 77. And so here is a much more elaborate, but we have figured out we're going to do, remember we do the random offset, it ended up with the number 13. We start at the 13 position, we grab 13, 14, 15, and 16, the bytes in those positions. Then we take the 13th, which would be the first byte, and we do a left shift of 24. The second one, we do a left shift of 16, and then a left shift of 8, and the last one isn't left shifted at all. And by ORing them, what we're essentially doing, if you can see from the back, is that we're taking 4 bytes and we're building them together to build one big number, which is going to give us enough digits to then get our 6-digit randomly generated number. And remember, the spec says anywhere from 6 to 10. So this will give us a number that's either 9 or 10 digits long. If it happened to be 9 and we needed 10, 0 would just be padded on the front of it. And so I just thought this was, again, really cool. And again, this could be done by, I don't remember what the first number is, but let's say it's 20 times 2 to the 24th, and then I would add 13 times 2 to the 16th and so on. It's the same as what we're doing here, but again, this is faster computationally, which is one of the requirements for the spec. And then the very last thing is just extracting the value. We have this longer digit, this longer number. We need 6 digits from it. And so we do what's called a modulo operation. So essentially that's doing a division by, so if you're doing modulo 10 to the 6th, and we're doing 10 to the 6th because we want 6 numbers, 6 digits, we divide by 10 to the 6th, and then you just take the remainder, and that is your number. So again, the modulo is faster than doing a calculation this way. So in summary, we started with a UTC time like October 23rd, 2018 at 21:03. We had a randomly generated secret key. We do these cryptographic hash operations, and we end up with a 6-digit number. And I think it's super cool, really interesting how it's combining hashes, very clever ways to generate, sort of randomly get these numbers, and pretty much impossible to reverse engineer, impossible to predict what the next number is going to be in the sequence. We do have some additional considerations. So a couple things. First is we need secure transport. And partly it's because, again, there's this one step where we're exchanging the secret key that's the linchpin of this whole operation. But the other thing is, just like password submission, submitting the token is susceptible to man in the middle. So we need to make sure we have secure transport. Also interesting, they specifically call out that this token cannot be used as a standalone factor. It can't replace passwords. It's meant only to be a second factor. We mentioned brute force already. It is possible to break this if we allow people to just enter those numbers, 6 digits, until they hit the right one. So we got to take that into account. We talked about clock drift already. They call out specifically that the device, that the token is stored, or the secret key is stored on, has to be secure. Luckily, most modern smartphones have some kind of a PIN or a thumbprint or something like that. Or these third-party tokens like the RSA key would have similar security on them that makes them really unusable to somebody who happens to steal it from you. And the last thing, again, if you've used this before, you'll see that commonly you want to provide a cookie-based do you trust this machine? And if you tick that, then you don't have to always enter that second factor. So maybe you do that on your home machine or something like that. Obviously, you want to be careful with that. You might do that not for your bank accounts, even on your home machine. Depends on how you want to manage it. But it is a usability thing to consider. You also need to consider recovery. And the most obvious is you lose your phone, you lose your token, or bought the new latest greatest iPhone and you need to switch to that. But another one that might happen is you're badly injured, you're in the hospital, and you have a power of attorney that you've authorized to pull some of your funds, and they need to be able to somehow do this, right? So some of the options are the Authenticator app itself might have a backup. So one of the reasons I personally use Authy is it gives me an option. If I absolutely need to, I can decrypt my secret keys, and then I can use the browser to generate my 6-digit number. You can always register a second device. So when you have the QR code, you could have 2 phones. Maybe you and your partner can both scan it at the same time. The most common thing you see, though, is that sites will offer a backup code or a series of backup codes. And this gets back to the one-time password option. So here you would be the advantages of just another, like, a security question kind of a mechanism. Who's your mother's maiden name or something like that. Here it's a randomly generated long password, and it's a one-time. So once the user recovers with that particular code, the code is no longer valid. So if a hacker somehow has taken them, the user might be able to do that and change their key or something like that. But this also might be a case where, all right, SMS isn't totally dead as a verification, or email. This might be a case where, all right, for this limited time, maybe we authorize a window of, yep, send them a text, get a code, then they can swap out their new phone, something like that. All right, so time to go into a short demo and a little bit of code. So let's make sure I still have these running. Yep, got my final space. And what I've got on the right is I just wrote up a little command prompt application, a console application, to pretend it's a mobile device, partly to show that this can be really, as long as you have the formula, you can do this on just about anything. But also to emphasize that one of the other advantages of this is that the mobile device does not need to be online. So a huge advantage over the SMS in that sense too. So I'll just come in here, register. I'll just run through this quickly. Oh, that's already got me prompted. And on the education part, here I'm just saying, hey, you might consider using a password manager. Here's some suggestions for ones. And I also have this tick box. So if you de-tick it, hey, you're decreasing your security. Are you sure you don't want second factor or, two-factor authentication? Again, just to start thinking about, why are we hiding all this stuff away from users? Let's put it out right in front of them. Get them to start thinking about this stuff, So I'll go ahead and register. And then sure enough, here's my QR code. So again, remember, this contains all the details that I need. And so to use this, obviously my console app doesn't have it. Instead of typing in the thing, I would never do this normally. I've exposed the actual QR, the actual URL. Paste that in. And so, but part of that, as you can see now, yep, I'm able to parse out the application, the username, obviously the secret key, how many digits. But that way my app can tell me, oh, this is your Dropbox, this is your GitHub, this is your Gmail, whatever. And a lot of them will conveniently let you know that, oh, your token's only good for a certain amount of time. So now I can enter in my 6-digit code, and now I'm verified, okay? And if I log out, now when I log back in, I'm prompted for a code, okay? And so again, I would just go into my app and enter the number it's given me and log in, okay? So that's how this stuff works. Or, this is the user experience that you would see. So hopefully everybody can see the code. This is a .NET Core application, web application, .NET Standard code for the actual multi-factor TOTP calculations. And I've got unit tests, so I'll have the link on GitHub. Kirk can share along, and if you want to pull the code and take a look in more detail, feel free. But I thought I'd show a couple of the classes. So here's the compute token. This gets called when we go into register, or again, it's time to log in, provide the second factor. And can I do it bigger? Yeah, thanks. Is that better? A little better? It gets to where it's hard to see the whole thing. There we go. Okay. So, yep, again, just a reminder, we calculate the time counter. We pass that counter along with a secret key in to generate our SHA-1 hash. We take the results of the SHA-1 hash, we get the offset, which is going to that last least significant byte and getting our random position. Then we use that to go in and do the truncation. That's where we go in, we pick the 4 consecutive bytes, and we stack them together with the left shift and the binary OR to get our final number. And then the last bit is the modulo computation to then pull out the actual remaining 6 digits, the least significant. And we can go into the code. And what I've done is I've put in, a fair amount of comments. So refresh your memory when you look at the code. This is the formula. You can see we're doing a subtraction, Unix epoch from the current time, getting the seconds, dividing by the step. So that's our first calculation. Then we're taking that number, turning it into bytes, and the method, this .NET method that gets the bytes, just needs to be reversed to make sure it's big endian. I rely on a known .NET library to give me my SHA-1 hash. So again, reusing something that's already there. I'm not trying to figure out how to do that on my own. Normally, I wouldn't have even figured out the rest of this, but to make it easy to see how it works. Here's where I'm just doing my binary AND against 15 to get my random offset of 0 to 15. And then in here is that calculation from the slide where we're doing the left shifts, 24, 16, 8, doing the binary ORs. And I didn't talk about it, but there is this also an AND against these max values. And my understanding is that is to deal with the year 2038 problem, which basically is that when you get to year 2038, somewhere partway through, when you're counting up from that Unix epoch of 1970, you run out of room in a 32-bit integer. The 32-bit integer is not big enough to go beyond that. And the specification for this TOTP clearly says it has to work beyond year 2038. And so I'm pretty sure that's what these ands are doing in here, is to make sure the number doesn't get too big. And then the last thing, here's the modulo operation. And then we do just pad to the left with zeros if we happen to have zeros leading, because we turn it into a string, and obviously it would normally just, it would truncate the zeros off without padding them and putting them into the string. Yeah. So that's the code. And then I mentioned unit tests. I just wanted to show that I've got there's more than I'm showing, but the spec itself for TOTP gives you 5 calculations. So it tells you, use the secret key, use this exact date. And if you do that, you should get this number. So I can run these unit tests. And so, for example, I could say, given the time, 2603 with the shared key, I should get the number 353130. And if I go ahead and run those tests, hopefully you can see the results, but I like to unit. Oh, and I keep having this problem. Sorry. I forget that I have to turn these applications off, or they're hogging my, they're locking my resources. So let me just make sure I've got all this stuff done. Yeah. Let me try this again. If it still doesn't work, we'll skip the last little bit. But no, didn't want to cooperate. I'm still learning .NET Core, so there are a few little nuances about how it gets its resources that I'm not used to. So anyway, we'll get back to the talk here. And again, you can run the tests on your own, but part of the reason I wanted to do that is to show that, again, part of being a good developer is you want to obviously test your code. And in this case, the spec gives you what you can use to make sure it's working properly. All right, oh good, got time. So at the end, I promised that we'd at least talk about a few of the things that are coming up. So I mentioned this spec's been around since 2011. And we're having advances in AI, we're having advances in quantum computing, and even just passwords people are struggling with. So what's coming to maybe get rid of passwords altogether, or give us other ways that are at least easier for a second factor? And the two that I settled on that are available but are still becoming more readily more common is, one's called the FIDO2 and WebAuthn standard, and the other is just the general terminology, as far as I can tell, is behavior recognition. So FIDO2 and WebAuthn, it's an alliance, the FIDO Alliance and W3C. FIDO stands for Fast Identity Online, and this are some open standards that are meant to get rid of passwords. And so it has 2 components. The WebAuthn is a web API that you can use to do the authentication, and then you have a client to authenticator protocol, which is how your device will interact. And if you want to learn more about this, more than I'm going to show you in a second, the PurpleCon conference coming up that Kirk mentioned, Benno Rice from Yubico company is giving a talk on this, WebAuthn multi-factor auth for everyone. So I couldn't get a ticket. There's only like 150, but they are going to live stream these. So I'd recommend, if this interests you, to give that one a watch. But at its core, the original FIDO specification was called UTF, and it's using public-private key challenge. So just like SSL, it's the same idea. It's the same general process. So you get a key, a fob of some kind. So like this Yubico company will issue these. And it already has a private key on it. And then when you authenticate against the host site, the site generates a challenge, and then through the private public key process, you end up getting a verification. And so some of the advantages of this are, there's never an exchange of that all critical linchpin secret key, because it's on the fob that you get. You never have to send that secret key anywhere. And the other thing is that you don't really need to enter a 6-digit number or anything. So it's even more useful. Basically, you plug it into your USB port, or I think some of them work over Bluetooth, and the site basically goes, oh, it just sort of auto detects, the challenge happens automatically, and you're authenticated. So it's even more user friendly. Disadvantages are you have to buy the thing, and there is no viable backup other than buying several. So FIDO2, what it's doing is it's saying, okay, that UTF thing I just showed you, that's the possession factor. It's adding in biometrics inherits. So it's actually combining two-factor into one. And the other thing is that it's saying, well, we don't want to force it to be in like a Yubico custom fob or something. We want it to be able to be used on a mobile phone that has, say, a thumbprint on it or facial recognition or something like that. So the idea is you log in, you authenticate against your device with your thumbprint or with your face. And then after you've gone through that, then it does the issues, the secret key challenge to the host. So you're combining the two factors into one step. But again, it's just fairly intuitive. It's just like thumb, oh, it's done. And then the custom YubiKey, very similar. I just pulled this from their site, but it's a little thing. You plug it into a USB port, you put your finger on it, there's your biometric, and then it does the rest for you. And apparently these retail for about 20 US. So there, it fits the cost recommendation back from the original specs. So that's the FIDO2. Behavior recognition is fascinating, but again, it's well beyond trying to describe it in much detail, but I'll just give you an idea of what they're talking about. So the idea here, they talk about how you establish a user profile of established behaviors. Now, I'm not quite sure how they do that. You get the sense that this wouldn't work instantly. You would need to accumulate some data about the user for a while to get whatever the pattern is, where they tend to log in from, or again, how do they use their mouse? How do they type? Those kinds of information. Obviously, it would have to collect a baseline before it could start saying this is unusual behavior. But this would be the inherence factor, because again, it's something about the user. It's rather than physically their thumbprint, it's how do they act. And the idea is to actually be able to identify cyber criminals. That's a good one. We want to, rather than blocking them like, oh, you can't find the secret key or something. It's like, no, we can actually identify it because you're acting differently. You're acting strangely compared to what we're used to. And so this is, sorry, this is about as big as I can make it. So I pulled this from the Azure Active Directory risk events site, page, excuse me. And this is an example of what we're talking about with the user profile. So we have things like impossible travels to atypical locations. So in other words, I've logged in up in Auckland, and 20 minutes later, hackers trying to get into my account from Christchurch. And so the system goes, no, there's no way. Even on a plane, they didn't get there in 20 minutes. This is a hack. Or they're signing in from, South Korea, and they're always in New Zealand. So what's going on? It's kind of like when you use your credit card overseas and you get a call. It's like, wait a minute, you normally don't use your card in the US. So is this really you? Or maybe it's known that their credentials were leaked, and so we're going, oh, we know those credentials are bad. If anybody tries to use them, it's probably a hack. Those kinds of things would be these risk events. And I'm sure this will be an expanding list as this gets better and better. And I first learned about this from a really cool .NET Rocks podcast titled Security for Nonprofits. And in this, they tell a story of a school that was being attacked by a hacker who was using a password spray approach. And because of this kind of risk event protection, they were able to detect this is atypical login behavior. And they were able to prevent the hacker from getting in, but the hacker had no idea that they had been detected. And they actually even had apparently some valid credentials, but because the pattern was wrong, they were able to prevent the hacker from getting in while simultaneously still allowing the students to get in. So they didn't have to lock the system down. Valid people were able to log in because essentially their inherence factor, their behavior was correct, whereas the hacker's behavior was incorrect. So again, I thought that was a super interesting peek at what's coming on the horizon with these newer and advanced technologies. And so that's it. Thank you. So again, I'm a senior consultant at Equinox IT. I'm not much on Twitter, but you can reach me through LinkedIn. There's my GitHub handle. Like I said, I'll share the link to the Prezzo, and the code will all be in GitHub. You can reach me by email or through my webpage, my personal page at the Equinox site. And yeah, any questions? Thank you.
We do have a couple of people watching online, but I've checked there's no questions.
All right.
So real people can ask questions. Present physical people.
That
Or we
behavior
can-
detection, is that the same thing that keeps asking me if I'm not a robot?
Oh, like the ReCAPTCHA, you mean?
Yeah. Is it gonna be
Um,
as good?
No, again, based on the story that they told, there was no awareness by the users or the hacker, whereas obviously you know when you're doing the ReCAPTCHA. But I think I would categorize ReCAPTCHA as almost just like a verification step. So, because it falls into, it's another something that you know. It's not a possession or anything about you that allows you to get past that. You know how to tick the box or figure out what the jumbled letters are or whatever. So it's more akin to a security question, like, again, you know, what's your mother's maiden name or something like that. Yeah.
You suggest as backup factors for the TOTP stuff, you say, for example, SMS or email.
Mhm.
But isn't that weakening the whole thing? Because basically you can just pretend you've lost your TOTP and
Yep.
you basically own the SMS.
Yes, absolutely. And so that's, again, one of the challenges, and one of the some of these articles are pointing out, like, some of the proponents for the new FIDO2 are saying, you know, the only way you can use the TOTP, you're forced into some kind of backup that is less secure. And that's why I was saying, if you were to use SMS, I would recommend, for example, that maybe it's combined with a lockout. So you go, essentially the user experience would say, to protect you, we will let you come in an hour or something like that. And that way, and meanwhile, an email gets sent to the actual user to say, hey, somebody's trying to get in through a backup method. Is this you? Something like that, or via email or some other mechanism, you go, yep, that's me. Go ahead and send me the text. Again, I'm not clever enough to think of exactly how that worked, but it would probably be something like that. But it's a very valid point, and it's a general, you know, concern in security in general, is that, well, how do you back up the, you know, the information that you need to get in? I need an administrative account to get into this. Well, where does that password go? Okay, well then how do you protect that password? And it's sort of, this can be a never-ending cascade. And in fact, it was either that one or another security talk for developers where they address some of that. And again, that's the people at Microsoft are say use the Azure Key Vault as a way, and the Azure Key Vault itself now has, you can, in Azure Active Directory, you don't have to have users. You can have sort of partial users or roles. I forget exactly what they call them, but the idea is that only those can even get at the Key Vault. So I think that's sort of the idea, is to figure out a way to around that. But also, I think it's the general idea of, at some point you have to just say what's secure enough. So you build enough layers in, and then you say that's what we can do. Yeah.
I think Facebook
But it's an
has
excellent
like
question. What's that?
Facebook has something like a phone a friend or something.
Yeah.
I don't use Facebook, but I think you can,
Mhm.
if you're locked out of your account, you can get people to vouch for you.
Yeah. And Google and actually GitHub, if I remember, are pretty good about that, where you are typically given several options. And I think that would be another thing I think I forgot to mention is, I think ideally is give people choices. And ideally we have a couple of different secure factors. So maybe the TOTP becomes the emergency backup, and now it's the you know, Yubico, kind of the FIDO2, or, you know, if you get a behavioral challenge of, wait a minute, you're in an odd place, then you could go, wait a minute, I can authenticate with my TOTP to prove that it's me.
One more question with Kevin, with the one-time password sheets, or just generally protecting against that FOB10 reuse.
Mhm.
How would you talk about how that gets stored? So if my FOB says 1, 2, 3, 4, 5, 6 now, or if that is my recovery one-time password, how that will be a valid number for my TOTP at some stage of the year, probably. How would you store that? How would you enforce that?
I'm not sure I quite understand your question. Are you talking about the backup codes that I mentioned? Or are you talking about the secret key that's used to generate that 6-digit number?
The backup code? Or
Okay, so the backup code is generally used as a password. So you wouldn't put the backup code in to replace your current key. It would be like, you go in and you get to enter your 6-digit code and you go, I don't have my phone anymore. I want to use one of my backup codes. And then it's essentially saying, give me a second password. But the difference is, first of all, that backup code was not picked by the user. So it's going to be a nice, long, random secure password. And secondly, once it's been entered and said, yep, that's a valid backup code, that backup code is invalidated from that point forward. So those backup codes would be stored in the same way as the secret key. They would be encrypted. They wouldn't be hashed because you have to be able to decrypt them to show them in plain text.
No, usually they're hashed though.
Do they? Oh, you're right. I'm very sorry. You're right, because you can do a hash comparison on those. Apologies. Yes. So they would be stored as hashed. Yeah. Thank you.
And like with, I think with Google, at least the backup codes aren't 6 digits, they're like 12 letters or something.
Yeah, they're typically.
Just like random.
Well, it's yeah,
I
it's
don't think that
it's like
Just pop
16.
up your ones from your password set.
Yeah. And actually, that's what I do when I get those. I store them in my password manager as my secure way to keep those backup codes. Yeah, but that may not be secure enough. Maybe that would be something you might want to store. But the flip side is, if I am injured or something and I need my son to be able to withdraw some money and pay for my hospital, he's got to be able to get at those backup codes. So it's a challenge. Yeah.
That's a good thing that you showed us in the demo code screen, that user might be seen to have two-factor authentication.
Mm-hmm.
But what if they don't take that column for the two-factor authentication? Are we still protecting them?
You mean in my demo?
Yeah.
Well, in there, then I would allow them to register without a second factor. So it'd be your standard password only protection.
Yeah, but they are,
So I would still be, I mean, I'd still would hash their password, but I'm protecting them to the best of my ability. But for example, what I can't protect them against is they reuse that same password somewhere else. So yes, absolutely, I do the best I can to architect a good, strong system. But if they refuse to use a second factor and they are reusing their password, I can't do anything. The advantage of the TOTP is I, as the host, as a developer, control that they will be getting a strong random key to generate that second factor, and it will be unique to the user and the site. So even if a hacker somehow got their password and that key, back to the compartmentalization, it's only that account that would be affected, only for that user.
Yeah, I liked how in your demo you made two-factor auth the default.
Yeah.
I worked for a company where we had millions of users, and we went to all this work to build the two-factor auth, and even the most critical users, which we had a subset of our users that we were marketing to, saying, please turn on two-factor auth, something like 1.7% of users had done it after 2 months.
Yeah.
Pretty soul destroying.
Yeah. And I think that again leads back to, can we just getting into these systems where we just sort of take it away from the users almost? I mean, the behavioral stuff and things like that, it's still in its infancy. They're going to have their problems, but I think the move tends to be, how do we make it easier and easier and easier for users, and less able for them to self-destruct through ignorance or fatigue or whatever. And I think the other thing is that, again, it's like anything else. If people aren't exposed to it and don't know what it is, they're not going to use it. And yes, yours is a case of even people who are well educated and should be in the know don't do it. But if we start seeing more and more and more sites where people can, gosh, I keep being asked about this multi-factor, what is this? At least some people will start to use it, And again, hopefully in the meantime, some of these newer things will come in that just make it continuously more secure and easier. Yeah.
Did you look at the second step, two-step verification? Like Google, for example, when you log in now, they don't prompt you for like a 6-digit number. They just ask you, You just try to log onto that website. And then
Oh, you mean
on your
the
phone, you say yes.
the notification on your phone?
Lets you in.
Yeah. I looked at that, and my understanding is under the hood, that's the same mechanism. It just makes it easier because you can just say yes, and what it does under the hood is it submits the 6-digit number that
Yeah,
is
I guess it's
calculated.
something like that.
Yeah. And I think the other thing with that is I think you have to use the Google Authenticator app itself. So I'm not sure though, to be able to handle that notification step.
Yeah,
I'm not
I
exactly
mean,
sure on that
in
one.
terms of usability, it makes it
Yeah.
really easy because you
Absolutely.
just have to say yes.
Yeah. But that's a good point because yes, even within this TOTP process, there are some ways to make it better. YubiKey has some older keys that do the TOTP, and it's similar. You know, essentially, it will automatically submit the number for you, so you don't have to type it in. And I believe the RSA ID might work that way. I think some of the older RSA secure IDs just display the number, and you have stuff to type it in. But I think some of the newer ones probably do it for you. But yeah, there are ways to make that less painful.
Well, the downside is you do need an internet connection on your phone, whilst with the TOTP you don't.
Correct. Yes, you're right. That's an excellent point.
Another good thing about the UV keys and stuff like that is that if they do it automatically for you, it helps prevent phishing. So
Mhm.
like if you get phished and you type in your username and your password, the phisher could also just present a 2FA into your 2FA code.
Yep.
Thing, and if you enter your 2FA code, they'll just send that as well. So like those UV keys are like, well, this is the wrong website, so I'm not going to automatically submit my 2FA code to it.
Yeah.
It's cool.
Yep.
I have one more question.
Sure.
Like, if the actual valid user uses the login credentials but is using VPN inside his device and he forgets to like turn off that device, but the behavior authentication says that your location is not correct when you usually use your device. So will he still be able to log in, or?
For the TOTP, absolutely, because the TOTP doesn't need a connection at all. But for the behavioral stuff, that last bit I was talking about potentially could, because they could say, oh, that's wrong. And that again would be, I'm assuming these are probably some kind of AI algorithm. So again, there'd be hopefully some kind of backup of it really is me. Then the algorithm learns that, oh, they also use this VPN IP or something like that, or they tend to use that. So we're going to not include that as a risk factor anymore. We're going to use different risk factors for that user because we can't go by the location, the IP location. Yeah.
Cool. I think that's a really healthy amount of questions. Thanks again very much to Kevin for preparing such a great talk. If you want to hang around for a few minutes afterwards, I'm sure he can take more questions one-on-one.
Sure.
And I'll just stop the broadcast there with a round of applause.